Welcome to lecture number 33. So this time, as we say, that the simplex model is useful, but it cannot really predict the difference in the line spacing, right, in the spectrum, as we saw in this particular diagram. You see, in this particular diagram, we see that the spacing between the consecutive spectral lines in the P branch, for example, okay, P branch, actually drops as V approaches the WE. So in this particular exercise, we also said that similarly with the R branch, the spacing rises. So the simplex model cannot actually reproduce the actual positions of the various transitions. So we need a complex model for the same. And remember that the actual potential was given by the Morse potential. Now, the Morse potential is actually something that is very complicated to begin with. So we used the harmonic oscillator, but the harmonic oscillator only does a very good job in the lower part where you see the blue part of the line. So the harmonic oscillator only works for lower vibrational energy levels. The rotation actually leads to stretching, so the rigid rotor assumption is not good. And enhanced vibration also expands the bond length, right? And it affects the moment of inertia. So therefore, there happens a coupling between the rotational and the vibrational energy modes. So as a result of that, we need a more complex model to describe the rho vibrational and the vibrational transitions, which we are going to do in this particular lecture. So let us look at now that what are the differences, okay, in the complex model. So the complex model is what we are going to do next. So the complex model, you know that we already said why it is not, why the complex model is not really, is required, okay, because the simplex model does a very bad job in certain cases. So because each electronic level, right, is characterized by unique Morse potential, okay, which basically represents a prevalent bonding mechanism. Okay, so we can actually therefore write the internal delta as E plus GVE. We'll say what each of these notations actually mean. JE. Okay, so TE is basically the energy for a given electronic state. Energy for a given electronic state. Okay, the subscript E that you see over here, subscript E, this actually represents a dependence, or identifies a dependence of of vibrational energy, vibrational and rotational energy modes. Okay, on electronic state. All right, on electronic state. Okay, and the subscript V, so the subscript V that you see here is a subscript V. Okay, this subscript V indicates that rotational energy mode, is influenced by the vibrational energy mode. load. Okay. So also this equation actually reminds us that even in the ground electronic state, okay, so let us look at this. Even in the ground electronic state, okay, when TE is equal to 0, okay, the combined vibrational, and rotational, okay, motions or for any diatomic molecules, okay, ultimately depends on the specific internuclear potential. Okay, nuclear potential describing its electronic configuration. Okay, so this is important, right? So it depends on specifically on the internuclear potential, right? That actually determines its. So even though the ground electronic energy is equal to 0, okay? So we have to therefore devise more realistic expressions for G, E, and FVJ. We need more realistic expressions. Okay, so that is a good thing. So we need more realistic expressions. So this could be essentially derived now. This could be derived by the specific by solving by the solution of the steady state Schrodinger wave equation. The Schrodinger wave equation. Okay, for a given Morse potential. Okay, for a given Morse potential. Okay, so that is what we need to do. So the Morse potential VR, if you recall, VE 1 minus E minus beta R minus RE, RB being the equilibrium internuclear separation distance. This is given for a given electronic state. Okay. Surprisingly enough, an analytical solution can be obtained by using a power series representation of the Morse potential, but it is very tedious mathematically. So the revised solution, but let us just see that what the revised solution actually gives us. So the revised solution actually yields quite a few things. First and foremost, okay, it reconstructs the basic rigid rotor and harmonic oscillator, okay, harmonic oscillator model, but now as some higher order terms which are not negligible. Okay, so if we forget all the mathematical intricacies, let us write down the solution. So GV is equal to omega E V plus half minus XC V plus half whole square, where V equal to 0, 1, 2, da da da. Okay, similarly, if Vj is given as Vj into j plus 1, E j square, j plus 1 whole square, j equal to 0, 1, 2, da da da. Okay, so where Bv is equal to Be minus some alpha E into V plus half. Okay, so this is the two expressions that we get. Okay, if we employ the more general Dunham potential, okay, which is basically a Taylor series expansion. About RE. Okay, we merely introduced higher order terms into these equations. Okay, so but these three equations are sufficiently accurate for most purposes. Moreover, they include all the important physical phenomena. Furthermore, each controlling parameter can be related to its Moore potential through a combination of varieties of things and supplementary equations. So let us see what those supplementary equations are. So omega E, for example, is beta HDE divided by 2 pi square C mu. Then omega XC is equal to H beta square 8 pi square C mu. dE is equal to 4 dE cube omega E square, and alpha E is equal to 6 dE square divided by omega E XE by dE minus 1. So the second, so if you look at the correction term, the second correction term, which is basically this one. This is the second correction term. Okay, the second correction term is represents vibrational and harmonicity. Okay, so Xe is therefore called the anharmonicity constant. Anharmonicity constant. So the typical energy levels for an anharmonic oscillator it can be shown by this particular thing. Just let me draw this for you. Okay, this is like draw this red. One single line basically. 0, 2, 3, like that. Of course, it becomes a little bit adjusted like this. So this is Morse potential with vibrational levels. Okay. And all this is for an anharmonic oscillator. Okay, so this is for an anharmonic oscillator. Okay, so so this is a sample example. Okay, so the harmonic oscillator is of course a useful thing in this lower part, this part of the Morse potential. Okay, so this is a useful approximation for lower vibrational numbers. Okay, now if you see the negative correction term, if you look at this expression now, let's again revisit this expression. This is a negative correction term, right? Okay. So this negative correction term okay. This negative correction term, okay, actually states the possibility of, you know, of, if you think about it carefully, of dissociation okay, at sufficiently high temperature. Okay, so this actually states that there is a possibility of dissociation at high temperature. When we employ okay, the more realistic Morse potential. Okay, so so the spacing between the consecutive vibrational levels actually decrease with higher vibrational quantum numbers. Okay, this behavior is quietly a straightforward, robust manifestation of the correspondence principle. Now you can see that the spacing, okay, between consecutive vibrational levels, okay, must actually decrease, with higher vibrational quantum numbers. Okay, so this is to replicate the classical continuum upon dissociation. Yes, dissociation. Okay, now if you look at this term now, which is basically the second, this particular equation, okay, and this particular term, okay, the second order correction term, okay, where dE is basically the centrifugal distortion constant. So there, dE is the centrifugal distortion constant. So remember that due to centrifuging, there will be a little bit of a change, okay, of the bond stretching and all those things. So this is the expression. Once again, it's good to have it in front of you. Okay, so this was the term that we were talking about. So it basically represents, so therefore D basically represents rotational, okay, centrifugal stretching. Okay? This is also a negative. This is also negative correction. Okay, because, okay, why it is negative? Okay, that is because, okay, enhanced centripetal acceleration at high rotational quantum numbers must increase the moment of inertia, thus therefore effectively reducing any rotational energy. Okay, so the correction term is negative. This term is negative since enhanced centripetal acceleration at high rotational quantum numbers, okay, must increase IE, okay, must increase the moment of inertia. Therefore, this leads to effective reduction, okay, of any rotational energy. Okay. So dE is not the same as the binding energy. Okay, so if we eliminate beta from here, this expression from beta, which is equations for this, you have a beta, and here you have a beta. So if you eliminate beta, we eliminate beta, okay, we find that the binding energy okay, is they represented by something like a dE is given as omega squared omega e xc. This is not the same as dE, okay, which is basically a rotational constant. Okay, so we find the binding energy can be replaced by this. Okay, this utilizes specific measurements of, this utilizes spectroscopic measurements of omega e xc. Specific spectroscopic measurements of omega e and xc. That is what it does. Okay. So finally, if you look at BV equal to BE minus alpha E into V plus half, okay, this expression, so this represents what we call the rotation vibration coupling. Okay, here the coupling comes from the influence of vibration and rotation. So it is the one way, basically, influence of vibration on rotation, and not vice versa. In other words, this essentially translates to a one-way coupling. Okay, so omega e by BE values are of the order of 100 to 1000, okay, implying many vibrations per rotation, per rotation, okay, but no rotational events, per vibration. Okay, the controlling effect of vibration on rotation is also given in this particular diagram. Okay, if you look at it carefully, which portrays an increasing bond length with the rising vibrational quantum number. This increasing bond length leads to an increase in the enhanced moment of inertia, which reduces the effective rotational levels. Okay, so that's the negative correction term involving the coupling constant alpha E. Okay, so again, alpha E is a negative correction term. Okay, so it is called a coupling constant. E called a coupling constant. Again, it is negative in nature. Okay, so just to write it, okay, if you look at the Morse potential, you will see that increasing bond length, okay, leads with rising vibrational quantum numbers. So this further leads to okay, enhanced moment of inertia, enhanced IE. IE therefore reduces effective rotational levels. Okay, so hence we get the negative correction term. Involving the coupling constant. Okay, so this is what we get. Okay, so we saw that therefore we, in this particular lecture, we saw that how the Morse potential can be used now to depict a more complex model for diatomic molecules. Next time we will do what we call the row vibrational spectroscopy. We also saw the effect of vibrational anharmonicity, the centrifugal stretching, the row vibrational coupling, all these things we saw in this lecture. We'll use all these things in the next lecture to investigate more into the row vibrational spectroscopy using the complex model. So see you in the next lecture.